All right. So in this problem, we have a reaction between xenon uh, and fluorine here to produce xenon hexafluoride. So we have different experiments where the concentration of xenon changes and the concentration of fluorine changes. And we have the initial rates in molarity per second for each of those trials. So again, what you want to do is pick out two experiments where one concentration is changing. So I'm going to look to see two experiments where the concentration of fluorine is the same. So it looks like fluorine of 0.20 and 0.20 is the same. I'm going to look in this column and let's see if there's a doubling of the concentration. So here the experimental data is set up so that one of the concentrations is exactly double of the other. So experiment 1, the concentration of xenon is twice that of experiment 3, and the concentrations of both are the same. And we have these rates for those two experiments. So what we want to do here is calculate the ratio of the rates. And so we want to take the reaction rate for the higher concentration one, which is experiment 1. And we want to divide that by experiment 3, which is the smaller reaction rate. Okay. So what we get here is 1.25 times 10 to the minus 3 divided by 3.12 times 10 to the minus 4. And what we get here is 4.001, which is, 4.01, which is about equal to 4. Now again, what we want to do here is refer to this table up here where we have the ratio that we've calculated and a corresponding reaction order. So if the ratio is 4, that's not the order is 2. So it tells us that this reaction is second order with respect to xenon concentration. So I'll just put that with a 2 there. Okay. Now we do the same thing for the other reactant. So in this case, we want to look for two experiments where this guy stays the same, xenon stays the same. So it looks like 0.75. The concentration of xenon is the same. And here, conveniently again, it looks like the concentration of fluorine is double on a case of the other. So we want to take these two experiments, 4 and 2, and take the ratio to find out the reaction order with respect to fluorine. So again, we take the higher concentration rate and divide it by the lower concentration rate. And so that's going to be the reaction rate 4 divided by reaction rate 2. So let's write that out. So the rate of 4 divided by the rate of 2 is equal to 7.03 times 10 to the minus 3 divided by 3.52 times 10 to the minus 3. And what we get here is 2.00, which, is about 2. Again, we refer to this table here. So if the ratio of rates is 2, it tells us that the reaction order is actually 1. So it's fluorine to the first power, or just fluorine. So we can write the reaction rate law now. The rate is equal to the reaction rate constant times xenon raised to the second power times fluorine to the first power, or just fluorine concentration. Okay, so that's our reaction rate law. Now to find the rate constant, so we found the rate law, now we need to find the rate constant. We do some algebra here and solve for that. So K is equal to the reaction rate divided by the xenon concentration squared times the concentration of fluorine. Okay, forgot the subscripts of 2 here for this diatomic gas. All right. So we plug in the concentrations here. I'm going to use experiment 1. All of that data we can plug into here. So the reaction rate is 1.25 times 10 to the minus 3 divided by the concentration of xenon squared, so 0.5 squared, times the concentration of fluorine, 0.2. Okay. If you punch that out on your calculator, you get a value of 0.025. Now, what about the units? Let's look at these numbers here and write those in. So 1.25 times 10 to the minus 3, that's molarity per second, or just molarity times second to the minus 1. In the denominator, we have the xenon squared, so molarity squared, times the fluorine concentration in molarity, so times molarity. So what that gives us is molarity to the second minus 1 over molarity cubed, right? So 3 of these go away, so what we have, 2 of these go away, so what we have is molarity minus 2 seconds to the minus 1, okay? So that's our final answer here for the rate constant. This is a third order reaction overall, where the sum of the exponents 2 and 1 is 3, and so it has these funny looking units here.